modeling of hydro systems, hydraulic structures, and hydroactivity. And he's working as a deputy director at the
Thank you, Prasad. First of all, I would like to congratulate all the organizers of this event. It's a very nice stage to present my topic. Today I am going to introduce you to the geohydrological model. Am I audible? So, first of all, I would like to have an overview of the audience. How many of you have actually done groundwater modeling or are interested to do the groundwater modeling in the future? Show your hands. Okay. So, how many of you have used mode flow? I think this is a more common one. Okay. So my presentation is a little bit will overlap with Yala's presentation, but I will try to keep it more simple. So, what is model? Why do we model things, for example, with the help of numerical modeling or any other kind of modeling? A model is actually a tool to answer questions, some very specific questions. It's a framework of assumptions, simplifications, and predictions that describe natural system and their dynamic behavior on the basis of physical processes and with respect to very important word, specific questions. Before modeling, we should have our questions in our mind, but we want to get answers. So, what is geohydrological modeling or groundwater modeling? There is not much difference between groundwater modeling or geohydrological modeling. In groundwater modeling, we usually just talk about the water and its flow, whereas in geohydrological modeling, we also take all other counts of, number of problems like transport problems, pollutants, and such kind of things. Groundwater modeling is a powerful tool for water resources management, groundwater protection, and remediation. Decision makers use models to predict the behavior of the groundwater system prior to implement any kind of project. Clearly, it is a simple and very cheap solution as compared to the project establishment in reality. So the main two type of models which we do in geohydrological modeling is simply flow models and transport ones. In flow models addresses the relationship between different components of groundwater flow and the resulting groundwater table. So in just simple flow models, we deal with the flow of the water only. In transport models, they are based on the groundwater flow. They describe the resulting transport of pollutants in the groundwater, including chemical reactions, radioactive decay, and the biodegradation. We can classify models or groundwater models according to four factors. The physical, we can classify the groundwater models according to the physics, dimensionality, solution method, and time. Let me explain you one by one. In the physical options, we will have to describe the physics of the model which we want to compute. Like whether it is a confined aquifer model or unconfined. whether there is mixing of fluids or multiphase fluid is happening or not. Are we going to take into account of the density effect? When I told about the salt water intrusion, then we have to take the density effects also. And whether there is some chemical reactions are happening or not, like in the case of transport models. And then we have to decide in what dimensions or on what scale we have to model our problem. Like there could be a 0 dimensions also in which we just calculate the regional balances. In the 1D, one-dimensional problem, there could be in which we just have one significant dimension of a model. Like in a column experiment, we just do it in one dimension. It could be 2D, horizontal or vertical, where wherever the significant problem is or the flow is. Or we can even do the 3D modeling also, in which usually we do the 3D modeling where our scale is very small and we want to go on the micro level. So the third kind of classification could be what type of method we are going to use. Whether it is an analytical solution, finite difference, finite volume, finite element model, and for transport there are other kind of models like random walk or method of statistics. And the third and the last kind of classification we do is on with respect to time, in which we decide whether this problem is going to be steady state problem or it's going to be transient one or the dynamic one. In the steady state means all the parameters are constant with respect to time. And whereas in transport or dynamic problem, the inputs or the outputs which we are going to get are depend on the time. So a little bit about the application of groundwater models, like what we can do with the groundwater models. First of all, we can calculate or have an idea about the quantity of the groundwater. We can use groundwater modeling to interpret the observed heads, determination of drainage areas for wells, like what are the influence areas of a particular well, and outlining of groundwater protection zones of wells, identification of catchment areas, and preparation for transport models. For example, if you want to model a transport problem, first we have to do the basic one, which is the groundwater modeling. And then we can use it to predict the groundwater drawdown and build up for natural and human interaction. Drainage, for example, if there is going to be some construction work, we can set up a problem where we can know in advance like what this construction effect would have on the groundwater. And if there is a disposal site, if we are going to build some hydraulic structures, we can see their effect on the groundwater in advance. And lastly, we can do the estimation of water balances, like how much water is going to recharge in the ground, what are the boundary flows, and what kind of well discharges we can estimate. And another part could be the groundwater quality, like interpretation of concentration data, mass balance of contaminants, natural degradation contaminants, immobilization of contaminants, and risk assessment. These are all kinds of transport problems which we can model. So these are the general steps involved in groundwater modeling. Actually, I think this is true for any kind of numerical modeling. First, we have to define our objective. I think it's not very clear, but I will read it out. First, we have to define our objective, like what are our objective of this model. Then we have to do the data collection. After that, we will map out a conceptual model, and then we will do the mathematical model. We will define our equations and boundary conditions, and and then we will design it in the computer, and then we run the model. Then we have to do the model calibration. Model calibration is a very important step. So we will know like our conceptual model or mathematical model is relevant to our actual problem. So with the results of our simplified model, we will compare it with the field measurements. And if our measurements and the calculations are within an acceptable range, we can go further, like model verification and then reporting. Otherwise, we have to go back to the model design and we have to optimize our input parameters. So now I will discuss about very little about the groundwater model, groundwater basics of groundwater flow, which Leila has already actually gone through. But just small discussion about the continuum description of aquifer. So when we model the aquifer, we do not model it on a very micro scale, like how the particle of water is going to flow through the aquifer or around the rocks. Actually, the continuum description of the groundwater flows does not consider the actual flow path in the pore scale, but an average cross-sectional volume flow. So it's a kind of assumption or it's a kind of trade-off which we do to simplify our problem. And then there is a very basic equation or law in the groundwater flow. This is Darcy law. Lelo also told you about this. Darcy law is the constitutive equation that describes the flow of a fluid through the porous medium. The law was formulated by Henry Darcy based on the results of experiments on the flow of water through bed of sand. So I will not include the equation just to get introduced. So these are the different types of aquifer. I think you have an idea now. There could be confined aquifers, unconfined aquifers, aquifluids, and that kind of stuff. So unconfined aquifer means the water table is open to the surface or near to the surface without any pressure, whereas unconfined aquifers, they are usually under pressure and they try to maintain their equipotential line. So, a very brief definition of the important parameters which we are going to use in the second half of my lecture. The hydraulic conductivity describes the ease with which a fluid, usually water, can move through the pore spaces. So it's just a measure of that. Then the effective porosity. It is the total porosity less the fraction of the pore space occupied by the soil particles. Actually, it is the volume of the whole volume and minus the volume of the particles. So it's the effective porosity. And then there is another parameter which is known as specific storage. It is the volume of water released from a storage per unit decline in the hydraulic head. So again, we can give the example of a sponge. Like if we press it, and how much water is going to release from there. So it's a we denote it with a specific parameter, which is specific storage. So this is the general groundwater flow equation which mode flow solves it, and then we can have answers. So this is basically a Darcy equation in three dimensions. So it's a partial differential equation. And to solve this, we have to give some boundary conditions and initial conditions. So whereas K is the hydraulic conductivity, and the subscript denotes different directions, and X is the head difference, and Y is the distance. So simply, this is the Darcy equation which Leila showed you. This is a general one. So we can have different forms of it. If we want to do it in one direction, then the other parameters would be followed. And if we want to do it in the whole dimension, 3 dimensions, then we have to have all the directions.
What's my question about confined?
Yeah, I think it is for the unconfined ones. because we do not have a pressure term here. And W denotes the volumetric source and sink. Source and sink is another.
It is for confined.
So W is the volumetric source and sink, and SS is the specific storage, the parameter which we talked about earlier. So to solve the partial differential equation, we have to give some boundary conditions. So we will have some solutions at the start or at the end of the equation, and then we can calculate it backwards and forwards. So solving the groundwater flow equation, which is a partial differential one, requires identification of boundary conditions to provide a unique solution. Commonly, there are three different types of boundary conditions which we use in geohydrological modeling or for solving any partial differential equation. First would be the Dirichlet boundary condition. The second one is known as Neumann boundary condition, and the third one, which is not very commonly used, but it is called Cauchy type boundary condition. In the Dirichlet type boundary conditions, we assign cells of our discretized domain with some kind of specific head where we know the potential or the head of water table is known. So this is yeah, sure. Yeah, okay. Flow is just a kind of volumetric quantity. It is flow is just velocity into area in a very simplified form. So flow is a kind of volume, how much volume is going of water is going to pass is represented by a volume or flow, we call it flow. And the head is kind of you can say it's a kind of potential, stored potential energy of water. And for example, water table is like this in the ground. This is the water table, and this is the head former, the height of water former data. Okay, so this is H1 and H2, and we say it's a head, like it's a potential energy stored here and the potential energy of water stored here. So water will flow from this head to higher head to lower head. So it's a kind of the level, you can say. So this is over time, particular time. So the three kind of boundary conditions I was talking about. The Dirichlet kind of boundary condition in which we know the heads. For example, we have number of wells in our domain, or there is a kind of river passing through our domain, and we know the head there or the height of water there. So we will denote, we can use the Dirichlet kind of boundary condition to specify the heads there in our domain. Another kind of boundary condition is if you know the amount of the rate of flow over time, discharge. If you know the discharge at any particular point, you can use the Neumann boundary conditions. And then there is the Cauchy boundary conditions, which is the which is also rate of change of head like flow, but it depends on the head. So if the head is higher, the discharge will be lower, smaller. It depends on the head. So mainly, most of the problems could be solved with the Dirichlet boundary conditions and the Neumann boundary conditions. So, for example, this is a simplified sketch of our hypothetical problem. There is a mountain here on the right side, and there is a lake on the top left corner, and then there is a river which is flowing from there, and we have some wells in the well field. So here we can you, if I ask you, like what type of boundary condition we can use on the like mountains. It could be Neumann or the Dirichlet. Neumann or Dirichlet conditions. Like we have, we know from the mountains there's some kind of flow is going towards our domain. So we know there could be a kind of discharge. So we can apply the Neumann boundary condition here, whereas on the river side, on the lake side, we know the heads, the levels of water there, and we can apply the Dirichlet kind of boundary condition there. So I'll just simply make it easy. On number 1 and number 2 points, we know the amount of flow which is we can measure it over the over time. We can use it if we want to model it. We can use it this Neumann boundary condition, and this is the end of our domains. This is the scale which we are going to take interest in. So here we will apply on the sides, on the bottom and on the top of the domain, zero flow, we assume it. And on the lake side and on the river side, we will make it as a Dirichlet boundary condition, where we assume that we know the head of the water. And another 2 important terms which we saw in the general equation also is the sink and source term. It's the term which mainly deals in our case with wells. For example, if there's kind of an extraction well there, we model it as a sink term. Okay, because the flow is going in the sink and we're extracting it from the domain. We call it as a sink. And if there is some kind of injection well, which we do not commonly use in groundwater modeling, but in the reservoir modeling or in the petroleum engineering, we use it frequently. Injection wells, then we can model it as a source term. Later on, we are going to have a hands-on problem solving on mode flow. So in the terms of mode flow, we have to apply for some representative numbers to model the different kind of boundary conditions. So if the boundary condition is inactive or no flow boundary conditions, in the mode flow specific terminology, for the mode flow only, we will give the value of 0 of that discretized domain, 1 to the cells on which we want to calculate the solution, and -1 as a Dirichlet or fixed head boundary condition. So just now I will move towards the mode flow software itself. And here is the problem which we are going to solve. This is a very simplified one, just to help you get introduced with the interface and different kind of options which we have in the mode flow. So here is our simplified problem. This is our domain, which is almost 2.5 kilometers long. And on the right side, we have a fixed head boundary condition. Like for example, there is some river is passing through. And on the right side, on the left side, we assume there is a no flow boundary condition. And whereas in the almost middle, 1,000 meters from the right side, there is a extraction well, and whose discharge we will assume at 0.005 meter cube per second. So we will try to model this problem. And these are the different data which is given, like horizontal hydraulic conductivity, effective porosity, and aquifer top and bottom. Okay. So before switching towards the mode flow, let me introduce the domain, like how do we discretize it, or with the specific of. For example, this is our domain, and then we will divide it into very small volumes. So to model it, so we will have we can give inputs and get outputs on different points. This meshing. This is called meshing. This meshing could be as fine as you want to go into the detail, or you can handle the computational cost. But it could be a trade-off between the accuracy and the computation cost. So just assume this is our domain on which we want to model. It's a 3D kind of domain, and we can model different layers, but specifically in this problem we just have one layer of the model. So the depth of the layer which we want to model is 15 meters. So we will assume this end of the domain as 0 and this end of the domain as 15 meter high. And here we have a kind of river where we have a fixed height of 10 meters. And somewhere here we have a well, extraction well. And here we have a no flow condition. So, do you have any kind of confusion about this problem? Is it clear? Okay. So let me now switch towards mode flow. This is the icon for Modflow. It's a freeware, but Modflow itself is just a logarithm, computer logarithm, which is used in many commercial softwares also. So it's not a software itself or interface itself. It's just a background code which are we going to use with the help of this freeware called processing Modflow. So our domain is 2.5 kilometers almost, and vertically we can have an idea, we can just model it long enough to have no effect of the top boundary and the bottom boundary. So first you just have to save it, your file in a folder. First of all, we have to tell the domain size or the meshing size in which we are interested. So we will just follow along this very order of this menu. Like first we will define the mesh size, then the layer type, whether it is confined or unconfined, and then the boundary conditions. Then we have to tell the different elevations. In this case, we just have one layer. So we will just follow the order of these menus. So first we will find the mesh size. As I told you in our problem, it is just a one layer problem, but you can model as many as you want, like 2 layers, 3 layers, and in what depth you want to go. And then you have to tell the number of columns and number of rows in our domain, like I mentioned on the board. So in this case, columns is just assume it as x-axis and rows as y-axis vertical. So columns could be of 51 columns with the size of 50, I think. This is almost the same size which we want to model, and we will model it on the both axes. Okay, so basically this is our domain in which we put different kind of conditions. So if you are happy with this, then just exit the editor here and then save the mess. So now the first step is done. Now we have to define what type of layer we want to model. So in our problem, it was unconfined layer, very top one layer. So we will just use this type. We will define this type here in the unconfined. Okay. And so the two steps are done. Now we have to define the boundary condition. So in our domain, so this is our whole domain, and we have modeled so this is our domain, and we want to model all the domain. We can, and on the right side, there is only one boundary condition which we have to worry about right now. It's a fixed head boundary condition on the right side. So it's what kind of boundaries, in mathematical terms, it could be called as Dirichlet boundary conditions or fixed head boundary conditions in simple word. And to define the fixed head boundary condition, I showed you, you have to assign value -1 in the mod flow. Okay. So on this side of the cells, I have to assign value -1. So just right click on this cell, and in the boundary condition value, we have to assign -1 because we know it's a kind of fixed head boundary condition. We want to give value there. So it is now just assigned to a single cell here, and if you turn on this button, you can just copy the properties of this cell to wherever you want. So just switch on this cell to duplicate the cell, and just try to scroll down here. So on all the cells which is now I am going through is being assigned the value of -1. You can see from here also. So just turn it off now and save it. Now we have defined the boundary conditions also, and every other cell you can see is now active. The default value here is 1. 1 means these cells are active and calculations are going to be done on them. But if you want to assign some no flow boundary condition, like there's no flow or inactive cell, you can right click on the cell and assign the value of 0. Okay? Then it could be modeled as no flow boundary condition. So, but right now we just have one boundary condition on the right side, which is known as fixed head boundary condition. So we will make it active again and exit. So we are done with this boundary conditions. Now we have to tell the thickness of the domain. So the top of layer, as it is mentioned in our problem, it is a 15 meter depth of domain. So we can define the top of our layer. There are a couple of ways to assign values to this cell. First, you can put the values one by one on every cell. Otherwise, you can just go to the value, and then there is an option reset matrix. If you want to apply some values to the whole of the domain, you can use this option, reset matrix. And this is, we are going, the top of layer is, we know, is 15 meters. We are zooming it. So now everywhere the value is assigned is 15. Save it. And in the same way, you can assign the bottom of the layer values, which is we are assuming here is 0. So just go here, value matrix, reset matrix, and assign the value of 0. So the bottom of matrix, we are assuming every cell is our assumption is this aquifer is very straight, and every cell on the domain is on the same elevation. So now we are almost done with this menu. Then we will go towards the parameters. So the horizontal hydraulic activity or initial hydraulic heads, actually we have to give the initial hydraulic heads also. So we are assuming the initial hydraulic head is 10 meters everywhere. So value, reset matrix, and 10 meters. Here we will give the horizontal hydraulic activity, and in our problem is measured hydraulic horizontal hydraulic activity is assumed to be 0.0005 meters per second. So again you will just go here, reset matrix, and assign the default value over the whole domain, which is 0.0005. And you can see the units also here. It's length over time unit, so it's meters per second. Again, we have to give the effective porosity. No problem, it is assumed to be 0.1. Effective porosity is basically the volume of voids in soil through which the water is going to actually flow. So it's a kind of percentage of the whole volume. So we are almost done with our very simple model. So now we will run it without the well and the recharge condition which we have, but just in order to see like if our model is okay up till now. So go to the models menu, mod flow, and just run it here. Have to check these two options. Okay. Simple as that. Now it's done. You can see the water levels, contours on all very simple model. Go to this PM bar. Just open your solution file here. Options and environment. So actually, now everywhere head is scanning with was actually the case. So up till now there is no result because we have not actually changed anything. The water level in the river is also 10, and everywhere on the domain is also 10. But now we will apply extraction well on the domain, and then we will see the drawdown curves of them. So just because in our problem you can see it is almost in the middle and 1000 meters away from the right side, which is almost I think 20 cells, because each cell is of 50 meters. Just right click here and give the amount of recharge or extraction which you have it on your hand. So we will assume it as 0.005 section. This is we have to give the minus sign here if the well is extractional. Usually we have wells here are extractional, so don't forget to put the minus sign here, which signifies the extraction of volume. You press OK here, so then save it. Okay. And then you can run the model again. Now it's done. Go to the results extractor and then read the heads now. So now you can see it's different. We can plot it also. Here you can see the water levels. Before we were assuming like there were or the water level was everywhere was at 10 meters. But after the application of extraction of this well, which is 0.005 meters per second, you can see the drawdown, water levels over the domain. So in the same way, you can also plot the drawdowns also instead of heads. Yeah, on the right side, we were assuming there is a constant head of 10 meters. Like there is a river flowing whose level is maintained throughout the domain of 10 meters. And initially everywhere also the head was of 10 meters. But after the application of extraction of water at the rate which we specified, there would be some drawdowns on the levels. So these are the levels which are being shown away from the well, like what level water is actually now. So these lines shows the levels of the points joining of the same level. For example, this was over ground level, and initially the water was here at 10 meters, and here we are zooming a datum of 0 meters, and then we put the well here, and from which we are going to extract some water. And after the extraction happens, there will be a drawdown of water level. So the like 10 meters is here, the level of the water would be reduced here, like 9.7 something, or 9.8, 9.9, and here would be 10 again, far away from the well or out of the influence of the well. So joining the same, these circles are shows the line joining the levels of the same points of the water. So we are seeing it from the above. So this is a very small representation. And you can also see the depth along the depth also. So that was the cross section, visible, and I'm doing is I want to show you the, for example, if you the drawline, I've just put the row number and column number of this cell in which we have designated a well. So here you can see a very small depression of the water level. Initially it was straight line, but after the establishment of the well, then you can see a small pond here. So I think you can do a lot of other stuff also, but this is a very simplified kind of steps which you can follow to establish a very small and simplified problem. Our problems, I want to give you kind of problems you can solve with this very little tutorial you can go through. For example, this is a problem where you have on the upper side again and hills, on the south side also hills, and there is a river is flowing from the center. You can just model it on the rivers. You can give fixed and restricted kind of boundary conditions. There are 3 wells around the around the river. Then you can see the influence of these wells over the river. So this is a kind of problem. Just an idea. So this is another kind of problem. Inflow of water into an excavation pit. For example, there is going to be some construction site where you have to excavate a large amount of soil from, and then there is a river alongside also. You can just have to discretize your domain and apply boundary conditions, and then you can see the drawdown. Another kind of problem is you can use it with the help of the same parameters and also. For example, here between the rivers like of the arc, it's very simplified any kind of hydraulic system in between the river or canal. You can just model it by giving the upstream level of the water, which is going to be on the upstream, and then on the downstream, downstream of the hydraulic structure. Then you can see the flow line and seepage and water. Following the same steps. Thank you.
We also have a secret, and after the secret, Dr. Javaid from the irrigation department is going to talk about how groundwater is managed or not.